Welcome. Today we are going to study the unit number 4, that is Queen theory of operation research and management for B final students. In previous PPT we have already shared the game theory, which is unit number 3. I hope you have gone through that particular PPT. Now today we will start the Queen theory. Now the Queen theory, the contents of this particular lecture will be as follows. First we will see the introduction of the Queen theory. After that we will see the different Queen models, and after that we will see the Queen systems and structures, notations, parameters, single and multi-server models, Poisson input, exponential service, constant rate service, and infinite population. Now let us start first, that is introduction. Now already you are aware of the queuing theory. Queuing is nothing but the making the line in front of the server for your turn to get the work to be done. Whether you are an entrepreneur, engineer, or manager, learning about queuing theory is a great way to be more effective. Queuing theory is a fundamental to getting good return on your efforts. Whatever efforts we are taking for improving your organization or institute or any shop, we can say that. Then, if you decrease the queue, then definitely you will be beneficial and you will get the more efforts. You will get the more profit out of that. And that's because the result your systems and teams produce are heavily influenced by how much waiting takes place, and waiting is waste. Minimizing this waste is extremely important, and it's one of the biggest levers you will find for improving the cost and performance of your teams and systems. So that means if the queuing is very much less, then only your customers will be get satisfied, and your organization will get benefited. You will be able to quickly understand common scenarios such as, if web traffic increases 30%, will the server get overloaded? That means if the queuing the line get increased, then definitely the whatever server is providing the service, that definitely get overloaded, and the burden will be takes place on that particular server, and that's why the efficiency of that server will get decreased. So should I buy faster disks, or should I just buy a few more of what I already have? What if I specialized tasks in my team and create a handoff between roles? Knowing how to think about these kinds of questions will help you anticipate bottlenecks. As a result, you will build your systems and teams to be more efficient, more scalable, high performance, low cost, and ultimately provide better service both for yourself and for your customers. And when you need to calculate exactly how much things will bottleneck and how much performance will suffer, you will know how to do that too. Now let us discuss about queuing theory. What is meaning of this queuing theory, and what are the different parameters of this particular queuing theory? Let us do that. Queuing theory is a broad field of study that focuses on the many nuances of how waiting lines behave. Queuing theory boils down to answering simple questions like the following: how likely is it that things will queue up and wait in line? How long will the line be? How long will the wait be? How busy will the server, person, system servicing the line be? How much capacity is needed to meet an expected level of demand? And if you rearrange this type of questions to answer other questions such as, how likely am I to lose business due to too long waits or not enough capacity? If whatever server we are providing, if whatever facilities we are providing for the customers, if that facilities are not enough, then what will happen? The customers will not wait for the long time, and there is chances that our customer may lose. And that's why how much more demand can we satisfy without creating an unacceptably long wait? Now here one one of the thing that is to worry about queuing theory is that queuing theory is based on the probabilities. That means just we can make the assumptions that line should be the length of the line should be this much, the customers in the line should be this much. So these are just the probabilities. That is no any fixed assumption we can make out of that, and that's why the famous Eric Bowman tweeted that not even God understands queuing theory. Queuing systems are non-linear. This is very big thing to worry that queuing theory is non-linear. Now what's worse is that they are unpredictably non-linear. That means we cannot predict how that non-linearity behaves and what exactly happens in the queuing theory. So let us study about this more in more detail. Now you should be aware about the hockey stick curve. That means here we can see that as the utilization of the server increases, what happens? The residence time, that is the waiting time, is definitely go on increasing. As the utilization becomes 100%, the waiting time becomes infinity. We cannot say that what will be the residence time or what will be the waiting time. And that's why this is the very famous hockey stick curve, which indicates the utilization versus residence time and the waiting time. Now let us study about some real life problems of the queuing theory. Your Kanban board. Here also we have to wait for Kanban board. Getting a coffee at the coffee shop, we have to wait for that. Your computer CPUs and disks, if you have to prepare or repair, then also we have to wait for that particular things. At the traffic light, we have to wait. When the captain says you are third in the line for takeoff, then also we have to wait until your turn comes. Your load balancer, pre-order the new iPhone, trying to pick the best line at the grocery checkout counter, merging onto the freeway, connection pulling, collecting railway, bus or movie tickets, exam form, or paying the fees at the counter. Also, these are the real life examples of the queuing systems. Now, overall, we can say that what is queue? A queue is a mechanism for increasing availability. A queue is a lie. Queue is a lie that says the system is available when in fact it's not available but might be in the future. So this is very important line about the queue. A queue is a mechanism for improving the system utilization. That means the explanation of this particular line is that whenever there is a queue, then what happens? The server will work fastly to decrease the queue, and that's why we can say that this queue is a mechanism for improving the system utilization. Unless and until there is queue, the server will not work efficiently. And if the customers present in the queue are very much less, then what will happen? The server will relax and it will work slower, and he cannot improve his utilization. And that's why we can say that queue is a mechanism for improving the system utilization. A queue is a mechanism that can improve availability. In overall, we can say that a queue is a mechanism that can improve availability, utilization, and throughput. Throughput is nothing but this is nothing but the output which we will get after some time, but at the expense of latency. That means latency is nothing but we have to wait for grabbing our work or receiving our work, and that's why that is nothing but at the expense of latency we have to get some output and resource consumption. We have to consume some resources also. So this is about the queue. Now why does queuing happen? Why do things wait in the queues anyway? Now, if suppose server is more efficient, he can do enough capacity to do the work. He is having enough capacity to do the work. Then also why the queues happens? So let us take one simple example to understand why queues are happening. Suppose a grocery store has a single checkout line and a single cashier. Okay. Suppose an average of one shopper per minute arrives at the line to pay for their groceries. Scanning, bagging and paying takes 45 seconds on average. Will there be a queue and waiting?